So in this lecture we will talk about torsion test, which is not that famous test, but still if you want to know the twisting moment versus the angle of twist instead of stress versus strain, then this kind of test is performed. And basically what you have is a cylinder or cylindrical component of any material. It can be metallic material or it can be non-metallic material, and it can be a solid cylinder or it can be a pipe or a tube, so it can be hollow. Why we use hollow is because you will have some changes from the surface to the center in the stresses and hence in the moment. So, and why will we have this change from surface to center, that also we will try to understand. But before that, if we have to find out what is the torsion moment, then we can calculate this, and this is the symbol which we use for torsion moment, and that can be calculated as the integration, definite integration from the center to the surface. And let's say that the radius of this tube is equal to A. So we are going from 0, that is center, to the surface which is at A, and we can calculate this by the shear stress which will develop because of torsion if you try to twist it. And so the shear stress into the radius into dA is the area. So using this you can calculate the torsion moment, and if you do a simple maneuver here, that if you take R out, then it simply becomes the moment of area, this part. So this part becomes polar moment of inertia, and so then you have correct formulation for polar moment of inertia for different kind of geometries, standard geometries, and you can use that formulation to find out the torsion moment. So then it becomes easier to calculate the shear stress, or if you know the shear stress, then torsion moment. So for instance, for a solid cylinder, the polar moment of inertia, which is shown by a symbol J, although we have read J integral, so don't get confused with that. So polar moment of inertia for a solid cylinder can be given by pi d to the power 4 divided by 32, where d is the diameter. So using this, if you want to calculate, let's say shear stress, then shear stress can be given as torsion moment into radius divided by polar moment of, so mt into r divided by polar moment of inertia, which is J, and J is that. So if you put it there, divided by pi d to the power 4, and 32 will go up, so this will become 16 mt divided by pi d whole cube, because r you can change to d by 2, right. So 2 and 32 will become 16, and this will become d whole cube, and rest of the things are there. So, and then again if you are doing it for a tube, for example, so for the tube J will be different, and if you put that formulation, if you put that formulation to calculate shear stress, then it will simply be 16 mt into d1 divided by pi d1 to the power 4 minus d2 to the power 4. What has happened here is that if this is my hollow cylinder or hollow tube, then d1 is the outer radius. So from the center to the outer surface, if I take that diameter, so that is d1, and if I take the inner diameter, then that is d2, and with that you have this formula for the shear stress in the tubes. So if for instance this length is L, and how do you perform this test, or what really happens in this test is this. So you have, let's say, a cylinder, a solid cylinder, and then you give it a twist. Okay, so you give it a twist in such a way, so if you have a line on the surface which is like this, so then you give it a twist. So this angle, let's say, is phi, and then that will be making an angle here, and let's say that angle is theta. So this theta is the angle of twist. Okay, this theta is the angle of twist, and this length is L. Okay, so if these are the dimensions, then you can calculate shear strain. So shear strain gamma can be given as this. You already know that the shear strain can be given as tan, in this case it will be phi, and phi in terms of theta can be taken as r theta divided by L, right. So this tan phi will become r into theta divided by L in radians. Okay, so this is a very simple calculation, and then once you have this angle of twist and you can calculate the moment, then what you get from the test, so what you do is you apply a torque on the system, or you rotate it so that you create this angle of torsion, and then you plot this. So let me go to the next. So then you plot this, torsion moment versus angle of twist. So you again get a linear part and then a non-linear part like stress strain diagram. So in this case also you can have a proof stress kind of thing. So this is in radians. So you can take an offset as we do in the stress strain diagram, where we take 0.002, so 0.2%. So you can take 0.2% offset and you can find out the yielding torsion moment. So that will be, let's say, mt naught. Okay, so we can do this thing in this test also, and then the question is that why do we do the hollow cylinder test and what happens from the surface to the center. So, if you imagine a hollow cylinder, and this should be clear from the formula itself. So, shear stress is, for our solid case, it was 16 mt divided by pi d whole cube, and as the radius increases, the shear stress decreases, right. So, this you know. So, even for a solid cylinder, so if I have a solid cylinder and my radius starts from the center and then it increases to the surface, right. So, if I take any point here, let us say, so that will be a ring. So, because I am working in polar coordinates. So, if I take any radius value of r which is less than your real diameter. So, let us say your total radius is a, so less than a greater than 0. So, in that case what will happen, any value between these two. So, starting from 0 you will be increasing the value of r. As you increase the value of r, denominator will be increasing, the whole thing will be decreasing. So, the shear stress will be decreasing as you go to the surface, right. And in the center you will have the highest value of shear stress, right. So, because of that, because of this gradient, people do a hollow cylinder test to avoid the gradual transition of the stress, okay. Because what is happening is that you are measuring the angle of twist at the surface by troptometer, okay, by troptometer. So, in tension test we use the extensometer, in this case we use troptometer. Using that you can measure the angle of twist, and this angle of twist will be different. So, if you take a ring somewhere there, then there you might have a different angle because the stresses are differing, because you might have plastic deformation in this range, right. So, what you want to do is you want to minimize the differences from the surface to the center. In order to do that, it is preferred that you make a very thin tube, so that you can minimize this change, this transformation from surface to center. But then if you have to be very careful, because if you make very thin sheet, then the material will fail because of buckling and not because of torsion. So, you do not want to make it very thin, so that you cannot perform the test, okay. So that is why you do the testing on a very thin sheet, and then in the standard you have proper dimensions for the ratio of what the diameter should be in comparison to the length, and based on that you can do the test and you can find out these relationship, and then we will talk about how we do the analysis part and what do we get from this test in the next part of this lecture. So, whatever we discussed, the formulation for the torsional movement and the angle of twist connection with the shear stress. So, this formulation, and so this is for maximum shear stress, and the shear stress for a tubular section can be given by this formula, where d1 is the outer radius and d2 is the inner radius. That is evident from this formula, because otherwise this will be negative. So these relations are valid as long as the material is deforming elastically, so in this region. But when the material becomes non-linear. So, when it starts deforming plastically, then we cannot apply this formula or this formula, which comes from this one only. So, we cannot apply this. So, what to do then? And therefore, we need to find out some correlation which works in the non-linear part, which is essentially the plastic material behavior. But before that, using the elastic formulation, we can calculate the modulus, shear modulus or modulus of rigidity from the elastic calculation. So, we have the formulation for shear stress, and we know that the shear strain can be given as R into theta by L, where L is the gauge length and theta is the angle of twist and R is the radius. This is for a solid cylinder. So, we can calculate shear stress, we can calculate shear strain. So, the slope between these two will be the shear modulus, and then again we are talking about if there is any component of machine coming into it, then you have to take care of that. So, but if it is the real shear stress and if it is the real shear strain, then the slope between them can be given by this formula simply, that shear stress is equal to shear modulus into shear strain. So, we can find that out by converting shear stress using this one and polar moment of inertia. So, and J is polar moment of inertia. So, we can find out the shear modulus. So, this information we can get from the elastic deformation part. From the plastic part, from the non-linear part of the torsional moment versus angle of twist curve, we need to address that and we need to find out what information can we get from that. To find out the modulus of rupture or modulus of shear, it is important according to the ASTM standard that the gauge length by diameter should have an approximate value of 0.5 and the diameter to thickness should have value of 10 to 12 in order to find the correct value of shear modulus, because we know that there is a variation, there is a gradient of stress from the surface to the center. So, to avoid that we need to maintain a standard ratio, because everyone will be doing it at a different ratio, and therefore the value of the shear modulus will be dependent on the size of the specimen, and therefore we want to fix that whoever tests the torsion properties of the material and tries to find out the shear modulus, that dimension of the specimen must be fixed. All right. So for the non-linear part, let us define that we define a parameter theta dash, which is actually angle of twist per unit gauge length of the material, and then we know that the shear strain can be given as R theta divided by L. So, this simply becomes R into theta dash. Okay. And now we can calculate the torsional moment with the formula presented before will be 2 pi integration of 0 to the maximum. So, from the center to the surface, so R is equal to 0 to R is equal to A. So, I will just write A and then shear stress into R square dr, right. And now let us imagine, because in elastic deformation we knew how the shear stress and shear strain are going to vary, but in this case we do not know because it is plastic behavior. So, let us assume that the shear stress follows a relationship with the shear strain defined by this some function, certain function, which is f of gamma. So, if we do that, if we plug this in the calculation of moment of twist or torsional moment, then we can plug that part. So, this will be 0 to now we have to change the limits also. Okay. So, this will become gamma A, because now we want to change everything to the gamma value and we are replacing R value. So, we have to do it in terms of shear strain. So, we have to change the limits, okay, and we will use this formula to change the limits to replace R with gamma. So, what we do is, so now this will be 2 pi and then tau will be replaced with f of gamma, and then we had r square dr. So, R will be gamma divided by theta dash, right. So, it will become gamma square divided by theta dash square, and then we have dr. So, what can we do about dr? So, d gamma will be theta dash dr, right. Or yes. So, then if we have to replace dr, we should write d gamma divided by theta dash. So, it will become d of gamma divided by theta dash, right. So, it becomes 2 pi 0 to gamma at radius equal to a, which is gamma a, f of gamma square d gamma divided by theta dash whole cube, right. So, because we are integrating with gamma, so theta dash is independent of that. So, we can take this part out of the integration and then we can put it on the left hand side. So, we can write MT theta dash whole cube is equal to 2 pi integration of 0 to gamma a and f of gamma into gamma square d gamma divided by theta dash whole cube. So, but theta dash whole cube is already gone, so only this part will be there, right. Now, we know using again the same equation that gamma a will be equal to a into theta dash, isn't it? Because we know that gamma is equal to r theta dash, and gamma at a value of, when radius is equal to a, then gamma is equal to gamma a. So, radius is equal to a, so that becomes a and theta dash, right. So, using this, if we have to change, now you can do it in a generalized way also, but let us look at the boundary values. So, what is the value when at the surface? So, when radius is equal to the radius of the cylinder. So, there we can write d gamma is equals to a d theta dash, right. And then we can plug this in this equation. So, if we do that, we can change gamma as a function of a theta dash, right. So, we need to solve this equation, right. In order to solve this equation, whatever is the value of this integration, we have to apply the upper limit minus the lower limit, right. So, the lower limit is 0. So, let us say that there is no part in this integration, we are not aware of the function here, but let us assume that this has no part which is a constant. So, and even if there is a constant which is independent of gamma, not as a coefficient, then that will be cancelling out, right. So, let us assume that it is a simple function, there are no coefficients involved which can cause problem. So, and that usually is a fair assumption, because we know what kind of behavior this can happen. So, we have seen in stress strain diagram we usually have this kind of behavior. So, something like this will be followed here also, right. So, if something like that happens, then what will happen? So, the integration value of this, where we will be replacing the value of gamma with gamma A minus, so let me write that part. So, if we do that, so just do not think about these two lines at this moment. So, MT theta dash whole cube will be equal to 2 pi, and then in the limits we will be having integration of f of gamma square d gamma at a value of gamma A minus same thing. So, f of gamma square d gamma at a value of 0 when gamma is equal to 0, right, or gamma at when radius is equal to 0. So, that means at the center. So, this is at surface and this is at center, right. So, whatever is this, the value of this function, we will be replacing gamma with gamma A. In this case we will be replacing with 0. So, this part will vanish. If there are any constants in the function, that will also cancel out. So, here in this part, if there is any value which has no gamma in it, okay. So, you can imagine that that will cancel. So, because those constant will be independent of gamma even in this part and in that part. So, let us say if there is something which is like plus 6, so that will be coming here also, and that will be minus 6, and that will cancel out, right. So, that part is not a problem. Then any value which has gamma in it will become 0. So, all those things will, so this term we can ignore, we can focus on this term and replace gamma with gamma A. If we do that, can we replace d gamma with A d theta dash, right? Because what we want to do is not that we want to integrate this, but let us do that. So, let us do the integration of that. So, what will happen? So, this will be 2 pi, and then f of gamma will become f of A into theta dash, because we are replacing gamma with gamma A, which is equal to A into theta dash, right. So, it becomes f of A into theta dash, then gamma square will become A square theta dash square, and d gamma we can replace with A into d theta dash, A into d theta dash, right. And it's still yeah, I think we have replaced everything. And still we will have an integration, right, because that we have not done. We have just replaced with the upper limit and we have not yet done the integration. Forget about the next part, right, and keep this in mind. And now what we want to do is, we have not done the integration because we do not want to do the integration. What we want to do is, we want to differentiate this. So, we want to differentiate this with respect to theta dash, okay. So, we want to do this, and now this integration part we can simply forget about that, because integration and then we are doing the differentiation of that. So, we can simply ignore integration, and we can keep these values. So, we will have 2 pi is already there, then we have A cube, then we have theta dash square, and then we have f of theta dash, yeah. So, this is what we have as the differentiation of torsional moment. So, but what this differentiation will be giving? this differentiation will be giving me the value of maximum shear stress, because not this value, but from this value I will be getting the maximum shear stress, which we can call shear stress at radius r is equal to a. So, that we can call as tau a, okay. And tau a will be, what will be the value of tau a? Tau a will be simply f of gamma, right, and gamma at r is equal to a is a theta dash. So, this will be this, right. So, what we can do is we can replace f, there should be a also. So, f a theta dash with this here in this equation. So, if we do that, what happens? So, if we do that, then we have d of mt theta dash whole cube divided by d theta dash equals 2 pi a cube theta dash square into tau a, right. And now we know the maximum shear stress, okay, because maximum shear stress will be happening at the outer surface of the material, and we know the value of tau a. I mean, we can calculate the value of tau a from this equation, okay. So, in order to do that, in order to find out the value of tau, what we need to do is we need to differentiate this, right. So, if we differentiate this equation on the left hand side, what happens is that, so you do the integration, you do the differentiation like a chain rule, right. So, it will be 3 into theta dash square into d of mt by d theta dash plus, and then if you do the differentiation of this, it will be simply, so you will have theta dash whole cube only, and then you will have d of mt by d theta dash, right. So, first I integrated theta dash and then I differentiated theta dash and then I differentiated the mt, and so I can open it in this form, and this will be equal to 2 pi a cube theta dash square tau a, and from this we can write tau a equals 1 by 2 pi a cube theta dash into dmt by d theta dash plus 3mt, right. And this is an important equation to find out the shear stress at the surface. So, maximum shear stress, we can calculate maximum shear stress from our torsional moment versus angle of twist diagram, okay, because this is the slope of that diagram and this is simply the value of the torsion moment. And so, all these parameters we know from the diagram, like a stress strain diagram we have theta dash mt diagram, and from that diagram we can calculate the shear stress, okay. So, what we have at different value of theta dash, you have different values of this. So, as you will be increasing the torsion, right. So, you take the specimen and then you give it a twist like this, right. So, as you increase this angle of twist, this value will be changing, and therefore, from this diagram of mt and theta dash, you will have a diagram of, you can have a value of tau a versus shear strain, which you can calculate at every point of time using this equation. Okay. So, we are getting shear stress from this equation and we are getting shear strain from that equation. So, what we are essentially doing is we are measuring the torsional moment, angle of twist, and from that we are calculating shear stress and shear strain. Okay. So the diagram of torsional moment versus if you plot angle of twist per unit gauge length, which is theta dash, and mt is mt as we plotted earlier. So we will again get the same linear part and then non-linear part like we get in the stress strain diagram. So what we have done from the previous diagram is we have just replaced theta with theta dash. So this is simply theta divided by the gauge length. So therefore the diagram is not going to change much. Only the angle of twist is going to decrease. So the scale is going to change because depending upon what the gauge length is. Okay. And of course this has to be in radians. So that part you have to always remember that when we plot this, the angle is in radians. So so if this is the diagram, and then let us say that the non-linearity starts somewhere here. So take a tangent here, okay, and then if this is the value, so we are talking about certain point, and this you can do at different points also. So this length is the length of angle of torsional moment at this point of time. So when we are here in this diagram, when we are at that point, then this is the value of mt, right? We have taken a tangent, so the slope, and then wherever it intersects the y axis, you draw a horizontal line, and then that point intersects there, right? And so this is B, let's say this is B, this point is C, and this point is D, okay? So where are we? We are at a theta dash value of this, right? So this is the theta dash value when we are at the point C, okay? So if you have to use the previous equation to find out the shear stress, which was given by the formula, so tau A is equal to 2 pi A cube theta dash dmt d theta dash plus 3 mt, right? This is how we calculate tau A. What we do is we can do the same thing at every point of this diagram. So remember this diagram is actually data points, right, at certain intervals, like we did in the tutorial for the stress strain data. So we have some data points, and from each data points we can calculate. So what are these data points? These data points are basically mt values at different theta dash values, right? And so using these two values we can calculate tau A at every point of time. So let us now focus on the point C, where we know the value of mt and theta dash. What is the value of theta dash? This, okay? So if this origin is O, then theta dash is the length OD, mt is the length CD, right, and dmt by d theta dash is the slope. So what will be the slope here? That will be BC divided by OD, right? So if you put all those things in the calculation, so can we do that? We can try doing that. So 1 by 2 pi A cube into theta dash is OD, dmt by d theta dash is the slope, which is tan theta, right? So the slope here is this angle, and tan theta is perpendicular by base. Perpendicular is BC, base is OD again, plus 3, mt is CD, right? So this cancels out, so we simply have 2 pi A cube BC plus 3 CD. So this is how we can calculate the shear stress at each data point. So when we are in the elastic domain, In elastic domain we have different formula for that. Okay. When we are in the plastic part, in the plastic part we have to apply this formula. So when we are here we do that thing, when for instance we are here. Okay. So what we do? We take a tangent there. So assume that this is not the maximum point, otherwise the slope will be 0. So it will be, let's say it has certain value. So then you take this length and divide it by this length, and actually you don't need OD because you only have to take BC, which is this in this case. So when we are at C dash, let's say, so this will be my B dash C dash, right, and C dash D dash will be this distance when we are here. So at each point we can calculate this, okay, and we can plot shear stress versus shear strain diagram. Okay. The maximum value of shear stress which you can get at this point can be given simply, because at maximum point you will have this slope is equal to 0. So B dash C dash will be 0. So you will simply have 2 pi A cube 3 CD or 3, so 1.5 into CD divided by pi A cube. Okay. So this will be the ultimate shear stress, a maximum shear stress, if you want to call it that. Okay. So this is how it will be, the calculation for the non-linear part, so for the plastic part. What happens in the specimen is, in the cylindrical specimen which is like this, the state of stress is different from what we have in the tension specimen. So if this is the axis of my cylinder and I am giving it a twist and I am doing the torsion test of it, then the stress condition has something like this. So the maximum principal stress will be in such a way, and the minimum principal stress will be in this way. So sigma 3, because usually sigma 3 is the minimum principal stress, and in torsion usually, generally, mostly sigma 2 will be 0. Sigma 2 is the second principal stress. It's not sigma 2 2, it is sigma 2, which is 0. In tensile testing it is not 0, but in torsion it is 0. So basically you have a biaxial state of stress. Okay. So where will be my shear stress? Shear stress is usually the resultant between the principal stresses, right. So if I take this 2, let's say, so sigma 1 is pointing in that direction, sigma 3 is pointing in that direction. So I will have a shear stress in this direction which will be parallel to this axis, right. And if I do it for these two, then I have sigma 1 in this direction and sigma 3 is in that direction. So again I have something in this direction, right. So the maximum shear will be happening like this. Okay, because that will be the resultant of the maximum principal stresses. Okay. Now these two can change also. So sigma 1 can be compressive, sigma 3 can be tensile. It can reverse, right? That can happen because positive negative value. So in that case, so what I am saying is maximum principal stress does not have to be on this plane, it can be on that plane also. Okay. So if we draw that situation, then we can have a situation where sigma 3 is this and sigma 1 is there. Okay. And in this case what you will have is you will have shear occurring. So we got the shear as a resultant parallel to the cylindrical axis. If we have this scenario, we will have perpendicular to the cylindrical axis. So shearing will be something like this. Okay. So, this will be the scenario, and as you know that shear stress causes the plastic deformation. So, dislocations they usually move because of the shear stress and not because of the tensile stress. So, if you have a ductile material which you are testing in torsion, then the sample looks very similar to a tensile sample. So, you have a grip and then this will break almost perpendicular because the shearing is happening like that. In tensile testing, if you remember, how was the shear stress? So, if the tensile test part was something like this, and in this case shearing will be in this direction. And in this direction, right. So, this is why we got cup and cone type of fracture. So, something like this and the other part was like that, and various combinations of these 4 directions, right. But in torsion you can either have a fracture which goes like this, but that is not possible. So, you usually for ductile material you will have a fracture which will be flat, but the surface will not be flat, surface will be fibrous, because again there will be dimples and all those things, but the overall surface will be perpendicular to the axis of cylinder. This will happen for ductile fracture. Okay. For brittle fracture, usually it takes the maximum principal stress for brittle fracture to happen, and that part we have discussed when we discussed about the probability of cleavage fracture or brittle fracture. So, in that case the fractured specimen will have a shape of a helix. Okay. So, it will have a something like this. Okay, and this part has a 3rd dimension. So, it will be, you can have a look at this kind of fracture feature in the book of Dieter. So, it looks something like this when it is brittle. Okay, because in brittle it will be failing because of the maximum principal stress, and in ductile fracture it will be failing because of the shear stress part. Okay. So, mostly this is all about the torsion stress, and there are certain differences in the torsion test and the tensile test. So, the most important difference in a tensile test and a torsion test is that in tension test the maximum shear stress usually is half of the maximum stress you have, maximum normal stress you have, half of that. But in torsion you will have tau max is equal to sigma max. Why is that? Because we have one maximum principal stress in compression, right. So, if you want to calculate shear stress, how do you do it? You do as a difference of maximum and minimum principal stress, right. So, maximum principal stress is sigma 1, minimum principal stress is sigma 3, which is in opposite direction. So, that is negatives, right. So, negative and negative will become positive, and if you assume that these two are same and is equal to sigma max. So, then it will become sigma 1 divided by 2. So, it becomes 2 sigma 1 by 2, which is sigma 1, which is the maximum principal stress, so sigma max. This happens in torsion, right. So, what is happening is for the same amount of maximum principal stress, more shear is felt in torsion rather than in tension. Okay. And because of that, the shearing, the ductile fracture will start first in a torsion test. You can delay the brittle fracture in torsion test. Okay. So, in tension brittle fracture will happen before, in torsion brittle fracture will happen before, because shear stress, in torsion you will have brittle fracture, so ductile fracture will happen earlier. Why? Because shearing is more in torsion, okay. And in brittle fracture, So, in tension shearing will be less. So, if the material is brittle, then that can fail easily, because shear stress has not achieved that high value in tension test. Okay. But in torsion test, shear stress will be double of what you will feel in tension. Okay. So, the ductile damage will start in torsion much earlier in comparison to tension. So, this is the prime difference between torsion test and torsion test and tension test. And with this we finish the torsion test, and we will talk about we will be dealing with a different topic in next lecture. Thank you.